Hello guys, today we will discuss about ethers. Introduction. Ethers are a class of compound having the general formula ROR, the 2R group attached to oxygen which is called ethereal oxygen, may be identical or different. Moreover, both these groups may be alkyl or both may be aryl, or one may be alkyl or other aryl. Ethers in which the 2R group are identical or referred to be a symmetrical or a simple ether, while those in which the two groups are different are called unsymmetrical or mixed ether. Thus we have CH3OCH3 dimethyl ether, symmetrical ether; CH3OC2H5 ethyl methyl ether, unsymmetrical ether. It may be recalled that ethers are a functional isomerism of a monohydric alcohol. For example, CH3OCH3 is a functional isomerism of C2HO5 as both have the same molecular formula, such that C2H6O but different functional group. Cyclic ether. Apart from ethers refers to above ethers containing oxygen as a part of a ring system are also known to exist. They are known as cyclic ether. For example, ethylene oxide, furanes, tetrahydrofuran. Cyclic ether contain three-member rings are particularly important and are termed as epoxides. For example, ethylene oxide CH2CH2O is a simple epoxide. Cyclic ether containing two or more oxygen atoms in the ring are also known to exist. Cyclic ether which have four or more oxygen atoms in the ring are called crown ether. They are generally named as X crown Y, where X is the total number of atoms while Y is the number of oxygen atoms. For example, a cyclic ether having 12 atoms involving 4 oxygen atoms known as 12 crown 4 is shown below. Nomenclature of ether. First, common system. Ethers are generally known by their common name, which are assigned by adding the word ether after the name of alkyl or aryl group present in a molecule or elucidated ahead. Dimethyl ether, ethyl isopropyl, ethyl phenyl ether. Second, IUPAC system. According to IUPAC system, ether are treated as alkoxide RO, derivative of a hydrocarbon. In case of unsymmetrical ether, the R group having larger number of a carbon atom is chosen as a part of a hydrocarbon, while the other group along with oxygen is taken as alkoxide group. For example, methoxyethane, 2-ethoxypentane, 2-methoxy-2-methyl-propane, cyclohexane, oxycyclohexane. Sometimes special names are also used for some of the ethers. For example, benzene plus OCH3 is popular known as anisole, while benzene plus OC2H5 is known as phenotol. Common and IUPAC name of ether: CH3OCH3, common name dimethyl ether or methyl ether. IUPAC name methoxymethane, and so on. Method of formation of ether. Ether may be prepared by the following method. First, Williamson synthesis. This is easily the most important and widely used method for the preparation of both symmetrical and unsymmetrical ether. It is carried out by the treating an alkyl or substituted alkyl halide with sodium alkoxide or sodium phenoxide. Sodium alkoxide plus alkyl halide give ether plus NaX. For example, sodium ethoxide plus ethyl iodine give ethyl ether plus NaI. Mechanism. The reaction involving nucleophilic substitution of alkyl oxide or phenoxide ion for the halide ion of alkyl halide, that is RONA equilibrium, RO negative plus Na positive. RO negative give electron to R of Rx and X release as X negative and ether form. For the preparation of methyl aryl ether, methyl sulfate CH3 twice SO4 is generally used in place of methyl halide. For example, sodium phenoxide plus methyl sulfate give anisole plus Na2SO4. Limitation of Williamson synthesis. The choice of alkyl halide and sodium alkoxide to be used in Williamson synthesis is somewhat restricted because of the following consideration. First, since a halogen attached to an aromatic ring cannot be easily replaced by the nucleophilic reagent, alkyl halides are generally used in Williamson synthesis. Therefore, in the preparation of alkyl aryl ether, the reaction is carried out between the alkyl halide and sodium phenoxide and not between aryl halide and sodium alkoxide. For example, as shown below, phenotols is a preparation by the reaction between ethyl iodine and sodium phenoxide and not between phenyl iodine and sodium ethoxide. Sodium phenoxide plus ethyl iodide give phenetols plus an AI. Diacryl ether are not generally prepared by the reaction. However, this reaction can be obtained by the reaction of alkyl halide with sodium phenoxide at high temperature in the presence of copper. For example, sodium phenoxide plus bromine benzene in the presence of copper at 583 to 603 Kelvin gives phenyl ether plus NaBr. Second, as a Williamson synthesis involves the attack of a strongly nucleophile alkoxide or phenoxide ion at the alkyl halide, elimination can also take place as a competing reaction to substitution. Now, tertiary alkyl halide has a greater tendency to undergo elimination than secondary or primary alkyl halide. Therefore, in the preparation of unsymmetrical ether, where there is a choice of alkoxide and alkyl halide, one should be selected the alkyl halide that has a greater tendency to take part in a substitution and a smaller tendency to undergo elimination. Therefore, primary alkyl halide, which has the least tendency to undergo elimination, are used in presence of two secondary alkyl halide, which is turn are preferred to tertiary alkyde. On the other hand, tertiary alkoxide are preferred to secondary or primary alkoxide. For example, in the preparation of ethyl tertiary butyl ether, we employ ethyl halide and sodium tertiary butoxide and not tertiary butyl halide and sodium ethoxide. Sodium tertiary butoxide plus ethyl iodide give ethyl tertiary butyl ether. Second, by heating alkyl halide with dry silver oxide, simple but not mixed. Ether can also be prepared by heating alkyl halide with dry silver oxide. For example, ethyl iodide plus Ag2O give ethyl ether plus 2AgI. Third, by dehydration of alcohol. When an excess of alcohol is heated with concentrated sulfuric acid or glycolic sulfuric acid at suitable temperature, 2 moles of alcohol lose 1 mole of water to form a symmetrical ether. Thus we have alcohol in the presence of H2SO4 give ether plus water. For example, ethyl alcohol at 413 Kelvin temperature H2SO4 give ethyl ether plus water. The preparation of ethyl from alcohol is always accompanied by the formation of alkenes due to the complete dehydration of alcohol. In case of primary alcohol, alkenes are formed only in small amount which can further suppressed by using alcohol in large excess. In case of secondary alcohols, alkenes are formed in relatively large amount. In case of a tertiary alcohol, alkene because the main product in place of ether. Therefore, dehydration of alcohol is used only for preparation in ether for primary alcohol. Mechanism. The mechanism of formation of ether involving nucleophilic substitution with the oxynium ion as a substrate and a second mole of alcohol as nucleophile. The reaction can follow either first order reaction or a second order reaction kinetics depending upon the nature of alcohol used. In generally secondary or tertiary alcohol reaction by SN1 mechanism, while reaction of primary alcohol follows SN2 mechanism. In both the mechanism, the first step involves the formation of oxynium ion. This is followed by the other step, which of course differ in two mechanisms as illustrated ahead. SN1 mechanism. Alcohol plus H positive give oxynium ion or a protonated alcohol. Second, Protonated alcohol slowly convert into carbocation plus water. Third step, alcohol O O's lone pair attack on R positive carbocation change into oxynium ion or protonated ether. Fourth, then O is electronegative atom, then there is no there is a loss of H positive ion and form ether plus H positive. SN2 mechanism. Alcohol plus H positive therefore forms protonated alcohol or oxynium ion. Second step, alcohol plus protonated alcohol या oxynium ion transfer into oxynium ether, then H positive loss form ether. Dehydration of alcohol may also be carried out by the passing of vapor of alcohol over a catalyst like alumina at a stable temperature. For example, alcohol in the presence of Al2O3 at 523 Kelvin temperature give C2H5O, C2H5 plus H2O. Limitation of this method. First, dehydration of alcohol cannot be used for preparation of unsymmetrical ether as it leads to the formation of complex mixture. Second, it cannot be used for the preparation of ether for secondary and tertiary alcohol because it leads to the formation of alkenes in large quantity due to the complete dehydration of alcohol. Third, the temperature of the reaction has to be carefully controlled to avoid complete dehydration of alcohols. Fourth, preparation of methyl ether by the using of diazomethane in the presence of fluoroboric acid. Diazomethane react with alcohol or phenols to yield methyl ether in excellent yield. For example, N-hexyl alcohol C6H13OH is easily converted into hexyl methyl ether by this method. N-hexyl alcohol in the presence of diazomethane in the presence of HbF4 give N-hexyl methyl ether. Mechanism: fluoroboric acid plus diazomethane give N-hexyl methyl ether. Fifth, oxymercutation demercutation of alkene. Oxymercutation demercutation reaction for the conversion of alkene into alcohol can also be extended for the preparation of ether from alkenes. For preparation alcohols, oxymercutation of alkene is carried out in water followed by the demercutation with NaBH4. For the preparation of ethers, alkene is treated with alcohol in the presence of muriatic acetate followed by demercutation with NaBH4. The product is known as oxymercutation demercutation, and its net result is addition of alcohol to alkene to form ethers in accordance with Marconico rule. For example, the overall reaction for preparing ethyl isopropyl ether from propene may be shown as follows. Sixth, by the addition of alcohol to alkene. Direct addition of alcohol to alkene in the presence of suitable mineral acid can also be used for the preparation of mixture ether in a particular. For example, 2-methyl-2-propene plus alcohol या methanol give in the presence of H2SO4 give tertiary butyl methyl ether. Physical property: ether can be regarded as organic derivative of water. In the presence of hydrogen atom has been replaced by alkyl group like water. The oxygen atom sp3 hybridized in ether in surrounding by 2 lone pair and 2 bond pair of electron. As such, ether are bent molecule in which the COC angle is nearly tetrahedral. However, the acute angle depending upon the size of a group attached to oxygen. For example, the COC angle in a dimethyl ether is 112 degree, while the dimethyl ether the angle is 118 degree. As the size of alkyl group increase, the steric repulsion interaction push the group apart so that the bond angle increase. The molecules of ether are weakly polar, with oxygen having a partially negative charge and each of the attract carbon having a slight positive charge. Due to bent shape of their molecule, the dipole moment of one CO bond does not cancel out the dipole moment of the other bond. The net result is the ether possesses a small net dipole. Example, dimethyl ether has a dipole moment 1.18 dB. The physical properties of ether are as follows. First, physical state. Expected methyl ether and methyl ethyl ether, which are gases at ordinary temperature. All other ethers are colorless, volatile, and pleasant smell liquid. They are highly inflammable. Second, boiling point. The weak polarization of ether does not affect their boiling point sufficiently so that their boiling point are close to those of alkane with similar molecular weight, but their boiling point are much lower than those of a corresponding alcohol due to the absence of H bonding between the ether molecules. Among themselves, the melting point and boiling point of ether increase with increase in the molecular mass. Solubility. Ether are freely soluble in organic solvent, although they dissolve in water also to be a appreciate extent. The solubility in water is probably due to the formation of hydrogen bonding between water and ether. Ether are very good solvents themselves. Density. They are all lighter than water, although the density increase with increase in molecular weight. Chemical properties. Ether are relatively unreactive compounds. They are stable toward active metal, alkyls, oxidizing agent, and reducing agent. However, they do undergo the following reaction. First, formation of oxynium salt. Basic character. Ether dissolve in a concentrated solution of a strong mineral acid to form oxynium salt. In these reactions, ether behave as Lewis base due to the presence of two lone pair of electron on oxygen. Thus, we have ether plus HCl give dialkyl oxynium chloride. The salts are stable at low temperature in strongly acid medium. However, they get decomposed by water to give back ether and the acid. Second, formation of coordinate complexes. Being Lewis base, ether form coordinate complexes with Lewis acid such as BF3 and AlCl3 and also combine with Grignard reagent. For example, ether plus BF3 give boron trifluoride etherate. Ether plus RMGX Grignard reagent give Grignard reagent etherate. Third, formation of peroxide or auto-oxidation. On standing in air or oxygen, particularly in the presence of light, ether are readily oxidized to form peroxide. The structure and composition of ether peroxide are not known with certainty. One of the composition structure is an shown below in case of ethyl ether peroxide. Ethyl ether plus oxygen give ethyl ether peroxide. The ether peroxide are unstable compound and decomposition explosively when heat. Their presence in ether can be detected by the formation of red color on shaking the ether with an aqueous solution of ferrous ammonium sulfate and potassium thiocyanate. Ether must be made free for peroxide being distilled. This can be achieved by washing the ether with ferrous sulfate solution or distilling over concentrated sulfuric acid. Fourth, cleavage of halogen acid. On heating with equimolar amount of concentrated halogen acid, particularly HCl or HBr, the ether link break to form an alcohol or phenol and an alkyl halide. Ether plus HX give RX plus ROH. For example, ethyl ether plus HI give ethyl iodide plus ethyl alcohol. The order of reactivity of halogen acid in the reaction is Hi, HBr, HCl. In the presence of excess acid, the alcohol first formed reaction with another mole of halogen to form alkyl halide. Thus, in that case of overall reaction may be detected as ether plus 2HIX give RX plus R-X plus H2O. Mechanism. The mechanism of reaction is believed to be as follows. First, Initially, the ether reacts with acid to form an oxynium ion or protonated ether as shown ahead. Second, the oxynium ion is then attacked by the nucleophilic aldehyde ion by SN1 or SN2 mechanism depending upon the nature of R and R group and the reaction conditions. Presence of primary alkyl halide favor SN2 mechanism, whereas secondary or tertiary alkyl group tends to react by SN1 mechanism. Thus we have SN1 mechanism as shown below, SN2 mechanism. Point of a cleavage. In case of mixed ether, the alkyl halide products depend upon the nature of group attached to oxygen. First, in the cleavage of mixed dialkyl ether, the alkyl halide is generally obtained from the smaller alkyl group. For example, ether, ethyl methyl ether plus HI give H3I plus ethyl alcohol. This can be explained on the assumption that the mechanism involving in the case is SN2 mechanism because of steric effect of large group X negative ion attack the smaller methyl group. Second, when the ether contains a primary or secondary alkyl group and a tertiary alkyl group, we get a tertiary alkyl halide. For example, methyl tertiary butyl ether plus HI give tertiary butyl iodide. This can be explained by the SN1 mechanism. The tertiary carbocation being more stable is produced in the presence of 1 degree or 2 degree carbocation. This leads to the formation of tertiary alkyl halide. Third, cleavage of alkyl aryl or diaryl ether. In case of alkyl aryl ether, the cleavage of aromatic carbon oxygen bond is much more difficult than the cleavage of alkyl carbon oxygen bond. Thus, the cleavage of such ether by halogen acid yield a phenol and an alkyl halide. For example, anisole plus HI give phenol plus H3I, methane iodide. The phenol is not converted into iodobenzene even with excess of hydrogen iodide. Diaryl ether are very difficult to cleavage as both carbon attach to oxygen as part of a aromatic ring. For example, phenol ether is not cleaved by HI even at 525 Kelvin. Ziehl method. Cleavage of alkyl aryl ether with HCl form the basic of Ziehl method for the estimate of alkoxy group such as methoxy or ethoxy. In such ether, a known weight of a compound is treated with excess of concentrated HCl. The alkyl iodide, methyl iodide or ethyl iodide formed throughout cleavage is treated with silver nitrate. The precipitate of a silver iodide produced is weighted from the amount of a silver iodide formed. The percentage of alkoxide group is estimated. Fifth, cleavage with sulfuric acid. When heated with dilute H2SO4 under pressure, ether undergoes cleavage and get hydrolyzed into alcohol. Ether plus water in the presence of dilute H2SO4 give alcohol. On heating with concentrated H2SO4, ether react in the same manner as with halogen acid to form alkyl hydrogen sulfate and alcohol. For example, ether plus concentrated H2SO4 give ethyl hydrogen sulfate plus alcohol. Sixth, halogenation. On treating with halogen in the presence of sunlight, ether are readily halogenated to form polyhalogenated ether. For example, ethyl ether in the presence of Cl2 at HV means sunlight give prechloric ethyl ether. If the reaction is carried out in the absence of sunlight, halogenation takes place at the alpha position only. For example, ethyl ether in the presence plus chlorine give alpha diethyl ether. Seventh, electrophilic substitution reaction. Beside the characteristic reaction of ether described above, aromatic ether such as anisole and phenolate undergoes aromatic electrophilic substitution like nitration, halogenation, etc. It may be recalled that the alkoxy group is more readily activated and orthopara directing. For example, first nitration, anisole plus HNO3 give orthopara nitroanisole. Halogenation. Anisole plus Br2 in the presence of CH2 non-polar medium give orthopara bromoanisole. Explanation: due to the net electron releasing result of its minus I electron withdrawing inductive effect and plus M electron releasing resonance effect, the alkoxy group increase the electron density around the aromatic ring, thus stabilizing the intermediate carbocation. This leads to faster electrophilic substitution. The orthopara directing effect may be explained in terms of contributing structure of the carbocation formed by the attack of electrophiles at orthopara meta position as shown below. It is apparent that the carbocation formed by orthopara attack are more stable than the meta carbocation due to the additional contribution of a particular stable contributing structure 1D and 2D respectively, in which each atom except hydrogen has a complete octet of electrons. As a result, orthopara carbocation are formed in the presence of meta ions, so that substitution occurs mostly at orthopara position. Thank you. This chapter is complete.